Good morning, students. I am your physics teacher, Miss Amruta Zadhov, ma'am. So, as we have done all the theory part regarding kinetic theory of gases and radiation, and we are moving towards the series of numericals which depends on kinetic theory of gases and radiation itself. So, as we have discussed two parts which are related to numerical, which based on KTJ and R. Now let's move towards the next part, which deals with the some new more numericals, which deals with this chapter. All right. So after looking at all the three parts, you will come to know that all the numericals which are there inside textbook, which are unsolved numericals, which are there in exercise, are all solved. Okay. So if any one or any two of them is not solved, then you have to solve, and if you are not getting it or you are not getting the answer or you have some queries regarding that, you can ask me in comment box. I will try to solve your query and I will give you the answer of that question. Okay, so in this part we are going to solve some numericals which are not there inside the exercise but which are rather than textbook. uh, so let's move towards our part, which is part 3 of numericals. So here we are going to solve the following numericals which are similar to the numericals which we have discussed yesterday. Some of them are new to you, we'll solve. Okay, so let's moving forward towards the first numerical. So let's see what is that and on what it depends. Okay, it depends on emissivity. All right, so let's move towards this numerical. A body of surface area 10 centimeter square and temperature 727 degree Celsius emits 300 joule of energy per minute. Find its emissivity. Why I am underlining that are the given things, and we are going to write all the given things of the numericals, and wherever it is necessary we are going to convert it in a single system. So let's see. A, which is 10 centimeter square. A body is given whose surface area is given, and we are going to find out the emissivity of that body. Alright, what is emissivity? E, which is emissivity, and it is given by the following formula, which is this. Okay, so let's try to find out that. So area is given as 10 centimeter square. Yes, we have to convert it into meter square. So it should be multiplied by 10 to the power minus 4. So it is here by converting. Alright. Now T 227 degrees Celsius. We have to add 273 to convert it into Kelvin. So we are getting 1000 Kelvin. Instead of writing 1000 Kelvin, it is easy to write down 10 cube. So as to find out the numerical value of 10 cube, it will be easy for us. So I am writing over here 10 cube Kelvin. So as dq by dt is given as 300 joule per minute. 300 joule per minute. But unit should be joule per second, right? So to convert it from joule per minute to joule per second, we have to divide this 300 by 60 seconds. Right, so by dividing 300 by 60 we are getting 5 joule per second. So this is dq by dt that we are getting, and then sigma is given, which is constant term. All right, so by using formula dq by dt is equal to E sigma a t raised to 4. All right, so let us write down. By substituting all the values, we are getting, instead of dq by dt 5, E will be as it is, as we are going to find out the value of E, sigma, area and t raised to 4. Alright, so we are getting E as 0.08. As value of E lies between 0 and 1, remember the range of E. So you are getting value in that range. It should be greater than 0 and less than 1. So you are getting value as 0.088. Alright, so this is all about this numerical. I hope you got that. So let's move towards the next one. So here is the next one. What is the numerical over here? Determine the pressure of oxygen at 0 degree Celsius if the density of oxygen at NTP is 1.44 kg per meter cube and RMS speed of molecule at NTP is 456.4 meter per second. What we are going to find out and what is given? Determine pressure of oxygen. We are going to find out pressure of oxygen whose temperature is given, whose density is given, and RMS speed is given. Alright, so by the given thing you will come to know what formula we have to use. What formula we have to use? We have to use formula for RMS. Alright, so let's see what are the given things. These are the given things. T 0 degree Celsius, rho, which is density 1.44 kg per meter cube, VRMS, which is 456.4 meter per second. Rho is nothing but what? Mass upon volume. So it is m by v is 1.44. So I have written again. VRMS, formula for VRMS is actually under root 3 RT divided by m, right? But I have written 3 PV. As PV is equal to RT, we can write in terms of pressure because we have to find out pressure. So I am writing this equation in terms of pressure. So this is what we are getting, which is under root 3 PV divided by m. By squaring both the sides, I am getting this equation. By shuffling all the constant terms and by shuffling all the terms, I am getting value for P. By substituting value, I am getting this value. Okay, so in some cases what we have to do is we have to derive formula. In this case also we have derived. As PV is not there, it should be RT over there. But why we have written PV over here? Because we have to find out pressure in this case. Alright, so T, there is no meaning of T over here. So I haven't converted. Alright, so it is for confusion. So you are getting this. Okay, this is very easy one. We have solved yesterday such type of examples, so this is very easy one. Alright, so let's move towards the next slide, which explains the next numerical. Which might be explaining the next term, which is the third numerical. Calculate wavelength in Armstrong unit, which is maximum for black body heated to temperature of 3727 degrees Celsius. In this, what we are going to find out? Remember the spectrum, the graph of it. What we have done in that graph, by increasing the temperature of black body, we have observed the peak of wavelengths, right? And the peak of the graph was shifting towards left. Shifting towards left means as the temperature goes on increases, in case of black body the wavelength goes on decreases. So that is nothing but the Wein's displacement law that was explained by scientist whose name is Wein. So he gives that law, Wein's displacement law. Why displacement is there? Because wavelength is displacing. Alright, so and in this numerical we are going to find out that wavelength in Armstrong unit. They have specified in which unit they want the answer. In Armstrong unit they are wanting the answer. Alright, which is maximum. So lambda max. Lambda max we are going to find out for a temperature of 3727 degrees Celsius. And Wein's constant is given. Alright, so let's write down given thing. 3727 degrees Celsius means we have to convert it into Kelvin. So by convert it into Kelvin, we are getting 4000 Kelvin. What we are going to find out? Lambda max. Lambda max meaning is wavelength at which energy is maximum. Lambda max means not maximum wavelength. try to understand it. This is not maximum wavelength, this is the wavelength at which energy becomes maximum. So that we are going to find out at what wavelength energy becomes maximum, right, by using Venn displacement law. This lambda max is b upon t. From what it gets, lambda max is inversely proportional to t. So to remove the proportionality sign, we have multiplied by b, which is Venn's constant. So you are getting this equation, which is lambda max is equal to b upon t. By substituting values, instead of b, I am writing this value 2.898 into 10 to the power minus 3 divided by 4000. It is very easy. It can be asked for 1 or 2 marks. It is very one step forward answer is there. So this may be asked for 1 mark or 2 marks also. So they have said that it should be in Armstrong unit. So what I am getting over here, it is 0.7245 into 10 to the power minus 6 that I am getting. Now to convert into Armstrong unit, what should be 10's power? 10's power should be 10 to the power minus 10. So minus 4 should be over here, so that it will be get minus 10. So by shifting the decimal point towards right for the fourth digit, 1 2 3 4, I am shifting this decimal point here, then I'll get 7245.00 into 10 to the power minus 10 meters. So as 10 to the power minus 10 is written over here, I can directly write down lambda max is 7245 Armstrong unit. Okay, so we have solved this type of example also. So this is very easy to find out. It may be asked for 2 marks, that I have told you. 1 mark is for formula, and half of a mark will be distributed in the following steps. All right. Okay, so let's move towards the next part. Yes, what is the next numerical is here? A 60 watt filament lamp loses all its energy by radiation from its surface. The emissivity of surface is 0.5 and the area of the surface is 5 into 10 raised to minus 5 meters square. Find the temperature of the filament. I hope you all know the filament lamp. It you can get the filament lamp of Philips also. That are the filament lamps. Some specified lamps are there which do have filament kind. Alright, so that kind of lamp is having 60 watt and it loses its energy by radiating to the surface. Alright, it is having 6 watt of filament lamp, radiating energy, and whose emissivity, what is emissivity? It emits light to the surface which is having value 0.5, and area of the surface to which it is emitting is 5 into 10 raised to minus 5 meters square. We are going to find out temperature. So let's see what is given things. dq by dt 60 watt energy is given, E 0.5 it is given, area 5 into 10 raised to minus 5 meter square is given. All are in the same unit system, so no need to convert to anyone. So just write down the formula, which is dq by dt is equal to E sigma a t raised to 4. Okay, by substituting all the values which are given in the example, we'll get this kind of answer. T raised to 4 is equal to 60 divided by 14.175 into 10 to the power 13. By solving this, what we are going to get? We are going to get this answer, 42 point. Now I want to give you a hint. If t raised to 4 is there, right, so you can't to the right side, power of 10 should be in the table of 4 itself, because we are going to take that root of right sides. Are you getting? That means if t raised to 4 is 14.32 into 10 raised to 12, it will be easy to find out t. How to find out t? We are going to take 4th root, that means 1 by 4. We are going to take 1 by 4. So root of 42.32, right? So if 10 to the power 12 is there, so it will get easy to find out its fourth root. What will be 10 raised to 12th fourth root? It will be 12 divided by 4. So it will be 10 to the power 3 itself. If that value was 10 to the power 13, so it will get very difficult, and that means 10 to the power 13 into 1 by 4, what will be that? It will be got very difficult. That means 13 by 4 will be very difficult. So if you are taking square root, if you are taking cube root, if you are taking fourth root of anything, right side's tens power should be in that table itself. If it is fourth power, so the things or the numbers which are there on the right side, which should have tens power in fourth table, in that table. All right, I hope you're getting what I'm trying to tell you. So this will be, by taking fourth root of this, will be 2.55. This is not 103, this is 10 to the power 3. I'm sorry for this. This is 10 to the power 3. So you're getting value as 2550 Kelvin. So this is the final answer. Okay, C, 10 to the power 3, because by taking fourth root, for 12 divided by 4 will get. So 4 3 is a 12. So you're getting 10 to the power 3. All right. Here is the next problem, which is fifth one. A small blackened solid copper sphere of radius 2.5 centimeter is placed in evacuated chamber. The temperature of chamber is maintained at 100 degrees Celsius. Try to imagine this kind of numerical. A chamber, evacuated chamber is there, in which copper sphere is placed, which is small blackened copper sphere. All right, so it is there inside a evacuated chamber whose radius is given, and the temperature of chamber is maintained at 100 degrees Celsius. Fine. At what rate energy must be supplied to the copper sphere to maintain its temperature at 110 degrees Celsius? Now what to do? We are going to find out the rate of energy that should be given to copper sphere, so that the temperature will be maintained at 110 degrees Celsius, not 100. We have to increase the temperature up to 10 degrees Celsius, but the temperature of the chamber is maintained at 100. So we have to give some energy to the copper sphere, so that it will try to emit energy inside that chamber, and after emitting that energy, it will get heat up. When it will get heat up, it will increase the temperature. So the temperature will increase up to 10 more degrees, that will be 110 degrees Celsius. So what amount of energy we are going to give, that we are going to find out. All right, so R is given as 2.5 centimeter, convert it into meter. T1 is given as 100 degrees Celsius, T2 is given as 110 degrees Celsius. I have converted it into Kelvin by adding 273 to both of them. Then what to find dq by dt? Formula dq by dt is sigma A T2 raised to 4 minus T1 raised to 4. Now you may have one query, that in some numericals I have taken E, and in some numericals I haven't taken E in formula of dq by dt. Why is it so? See, here it is given as sphere is black body. In case of black body, what is emissivity? E, it becomes 1. So I am not taking value for E over here, because it becomes 1 in case of black body. And in formula, it is actually T1 raised to 4 minus T2 raised to 4. But there is a condition, if T2 is greater than T1, so you can take this kind of bracket over here. All right, so I am taking this. You may have query after going through the textbook. You may have this query. So this is the formula that what we are going to use, and by using which we are going to find out dq by dt. So by substituting value of sigma, value of area, now what will be area over here? Area is not given, as they have told sphere is there and radius is given. What is the area of sphere? It should be 4 pi r square. So I am writing directly over here as 4 pi, value of pi is 3.14 r square. I am writing over here 2.5 into 2.5 into 10 to the power minus 4 into bracket this 383 raised to 4 minus 373 raised to 4. By solving all this, I am getting this 0.977 watt. So this much amount of energy should be given to the copper sphere, which is we are going to consider as black body, by which it will emit energy inside the chamber, and the chamber will get absorb the temperature, and the temperature will rise up to more 10 degrees. That means it will be take 110 degrees Celsius by applying energy of 0.977 watt. Okay, so this is all about this numerical. So I hope you all get all the numericals which we have done from yesterday till now. We have done almost 15 numericals. In each part I have took 5 numericals, and these numericals are there inside textbook and outside of the textbook also. So try to write down this into your notebook. Not try, you have to write down these all numericals inside your notebook so that you will get practicing. All right, numericals are the part which you cannot just read, you have to solve it by yourself, then only you will come to know how to solve it. Okay, so this is all about the chapter, and here I am declaring kinetic theory of gases and radiation is finished with theory part as well as with numericals. If you have any query regarding theory as well as regarding to numericals, please do let me know. I will try to find out the solution of your problems, the solution of your queries, and go and first solve the quiz so that I will mark your presentee for today. All right, so thank you so much for watching all of my video which are for KTGNR. Okay, thank you so much.